So now we're going to look at why this would be happening, why this, the fact that whenever we take a non-zero number in mod 7 and we raise it to the 6th power, that we end up getting 1. Okay, so let's just look at a very particular example. Let's look at 5, or 5 bar as I'm writing it. Notice I'm not writing the bars in the tables because it's just a lot harder to do that in Excel. But over here, I'm trying to be consistent about writing elements of Z mod 7 with the bar over them. So I'm going to take 5 bar and I'm going to raise it to the 6th power. And if you just calculate that out, you know, somewhat laboriously, you get 1. That's this entry in the table right here. So why is that, and why is it universally true, seemingly, for that whole row? Okay, so there's various proofs of this, but I'm going to emulate the proof in the book, and that's to go back to multiplication. And this is a really common strategy. When you want to understand exponents, just think harder about multiplication, because after all, exponents are just defined by repeated multiplication. Okay, so we've got this multiplication table, and here it is really helpful that we're totally ignoring the zeros, and we're really focusing on just non-zero elements. And we just look at the multiplication table, the 5 row of the multiplication table right here, and we see that 5 times 1 is 5, 5 times 2 is 3, 5 times 3 is 1, etc. And there's a really, really important fact that comes from chapter 8, which might not have seemed incredibly important at the time, but now is becoming very, very, very important, which is that every non-zero element of Z mod 7 appears exactly once in that row. So that's really more for a different video, or going back to chapter 8, but really briefly, it's because when you are multiplying by 5 in mod 7, you can undo that. There is a multiplicative inverse for 5. And so there's a couple of consequences for that. That says that if I have 5 times x equals 4, I can solve that equation. So there must be something to multiply by 5 to create a 4. So the fact that you can solve the equation means that every non-zero element is going to show up here. And it's also true that if I try to solve 5 times x, let me write that out. If I wrote like 5 times x equals like 3, let me put the bars on. I don't want to go into this in too much detail. As I say, it's for a different video, really. But if I try to solve that equation, the fact that there is something that will create a 3, namely, it turns out to be 2, says that yes, 3 will really actually appear in the multiples of 5 row. And there's also another fact, and that's that there's only one x that solves that equation. You can essentially divide by 5. You can multiply by the multiplicative inverse of 5, just roughly like you would solve an equation with like real numbers. And you will get one and only one solution. That is part of why this number 3 can only appear once. It's only true that 5 times 2 is equal to 3, mod 7. Nothing else will give you a 3. So it's really about a fundamental property of this equation. It's about existence and uniqueness for this most basic equation. 5 times x equals something, okay? And that's a really cool thing, very, very general thing mathematically. Okay, so let's assume that that's really something we believe is true, that every non-zero element of Z7 appears exactly once. That is the key. And then just a little clever manipulation is going to do it. Now, these steps I don't think are super obvious. I think it would be hard to come up with this proof on your own. But given this fact, and one more cool fact about modular arithmetic, and then a clever trick to do with these numbers, gives us the result right away. Very much like in the book. So we're going to multiply them all together. That's kind of a funky thing to do. But you can multiply all those equations together. Here's the left-hand sides multiplied together. Here's the right-hand sides multiplied together. Okay, and I'm just going to regroup everything. Hey, guess what? The reason that it was a good idea to multiply them together is that that's a funky way to get 5 to the 6th power. But of course, it's also multiplied by 1 times 2 times 3 times 4 times 5 times 6. It happens to be in that order when I regroup, most naturally. Well, that's equal to the product of all the non-zero elements of Z mod 7. They came out in a different order, but all this is commutative. And so that's just the same thing as 1, 2, 3, 4, 5, 6. Now, the last step does require some thought and a real theorem, The fact that we can actually cancel, we can divide by this number, 1, 2, 3, 4, 5, 6, is not trivial. And again, that's one thing that would not work if we weren't in a prime mod. Okay, so yeah, let me make sure I emphasize, because we're in a prime mod, or more generally, because 5 is relatively prime to 7, that's why Theorem 8.3.6 was working. Really important that it's not absolutely general. But we're in a prime mod, and the 5 is not congruent to 0, and so we're good. And again, 8.3.2, when we can cancel is when the number we're looking at is relatively prime to the mod. And the great thing, of course, is that if we're in a prime mod, everybody but 0 is relatively prime. So we can cancel this 1, 2, 3, 4, 5, 6 on both sides, and we get 5 to the 6 equals 1. So it's very, very general. What we've used is that only that 5 was non-zero, a non-zero element of Z mod 7. And we haven't used anything really, really special about 7, except we did crucially use that 7 was prime. We're going to generalize this and see what we can say in the next couple sections when the mod isn't prime. It's going to get a little more interesting, a little more complicated. But this is the big realization, is that when the mod is prime, something really good happens. So we've got that 5 to the 6 equals 1, in a way that if we just change the numbers here and just use these two observations that are going to be true in any prime mod, Theorem 8.3.6 and the cancellation property 8.3.2, we basically are looking at the sketch of a proof in general. Now remember, if you're going to write down a proof and call it a proof, this is not enough. This is enough to get your creative juices flowing. You really want to write it down in full generality. But this should convince us that there's really something going on here. Okay.